in the 18th and 19th century, there was a very important guy, namely Jean-Baptiste Joseph Fourier. And he lived from 1768 until 1830. And he proved something very interesting. He showed that you can rewrite a sinusoid as complex exponentials as we have seen before. But what he proved with that was, if we have a sinusoid or a signal that is periodic, so it is reoccurring, it has a reoccurring pattern, any signal that is periodic can be rewritten as a sum of complex exponentials. And this is a very, very interesting property. And how to do this, how to get those complex exponentials. So given a sinusoid, so if we have indeed a sinusoid, and we go towards complex exponentials, this is called Fourier analysis. And of course, if we go back from all these complex exponentials to a sinusoid, this is called the synthesis, Fourier synthesis. And this is a very, very important property. And how to do that, we'll actually show you an example with a nice visualization. Normally, I wouldn't do exercises that are already in the syllabus, but for this one, I have a really nice visualization that shows that every periodic signal you have can be indeed rewritten as a sum of complex exponentials. So, we saw in the last video that if you have a sinusoid, you can rewrite it in the following form. We can take the sum from k from minus n up until n of ak times e to the power I times 2 pi times fk times t. And what Fourier says is, well, with each, it doesn't matter what sinusoid I can give you, you give me, if it's periodic, even if I have to take infinitely many exponentials or complex exponentials, I can still give you the sinusoid as complex exponentials. That is possible. And he calculates these complex amplitudes in the following way. He is saying, if we want to know A0, so the very first complex amplitude, it is 1 over T0, so we need the fundamental period, and we integrate over that period of just our function, just our sinusoid. And if we do that, we get our fundamental amplitude. For every other amplitude, we have to look at different frequencies that we can see in our sinusoid. So how we do that is 1 over T0, same thing, from 0 to T0 from our function xt, but now we also multiply this with e to the power minus I 2 pi over T0 times k times t. And remember that actually 1 over T0 is the same as F0, and F0 times k is also denoted as Fk. So this is actually in this here, this power of e is actually the same thing as here. The only difference is that there's a minus in front of it. That's the only difference. Now, he says, using these integrals, you can evaluate your sinusoid. Just give me a sinusoid, and with these integrals, I can give you all the complex exponentials to represent that sinusoid. So, badass that Fourier was, let's prove, or not really prove, let's show an example that he's actually correct. And after that example, I'll give you a nice visualization that shows you that this is true. So, if we have an example, and let's take as an example the square function. And the square function is denoted by the following. It's a 1 if our t is bigger than 0, but still smaller than half of a period. And it is 0 if and only if our t is bigger than half of a period, but smaller than the whole period. So if we were to draw this, what we would get is that it would go up here, up until 1. So if we draw the y-axis here, this is 1. It would go further, and then it would go down. And this is then, we could call this 0, but it is arbitrarily where it would be. This would be half of a time period. And then here it would be a whole time period where it would go up again. So we have indeed a pattern which is periodic. So this would be 1.5 t0 then, and then here again we would have 2 t0, etc. Like I said, this 0 is arbitrarily, but we could indeed draw the y-axis here as well. It doesn't matter. So we have this square function. It can be easily seen that this is not a sinusoid, because a sinusoid is nice fluently, and this is just square. And this is also why it's called the square function. But we can still calculate with it, and we're going to show that we can have infinitely many infinitely many complex exponentials to represent this function. First, we're going to calculate the fundamental complex amplitude. We do that with 1 over t0 times the integral, but we're not taking the integral up until t0, we're taking it up until a half t0, because what we're just doing with this function is just we're looking at the surface of this. But if we take the surface of whole t0, that means the surface of this part as well, but there is no surface there. So there is no real reason to take that into account. So we just have to look until half t0, which is nice. Up until this point, our function outputs a 1. So we just have to integrate this. Now, integrating this means that we have to do 1 over t0, and the 1 integrated is t, and for t we fill in as 0 or a half times t0. And this is equal to 1 over t0, filling in for t, we get half t0 minus 0. And as you can see, this is equal to a half, because t0 will cancel out with the t0 in the denominator there, and we're only left with a half. That's good. Now for ak, all the other complex amplitudes. We get the same thing, 1 over t0, and because right now we are looking at each pattern next to it. And to visualize that, we're looking at this one, and the following one, and the following one, etc., etc., etc. We want to know the amplitudes that we need to give our complex exponentials in order to represent this function. So again, we're going up until a half of t0, because each pattern, we only need to look at the first half, because that's how our square function is defined. And we get 1 times e to the power of minus I 2 pi divided by t0 t kt, excuse me, times k times t dt. Now we're going to integrate this, and integrating an e power is the same as deriving its power and putting it in front of it. So let's just write it down to the right here. A small rule. If we have the following, if we're going to integrate a times e to the power bx plus c, for example, 2x. If this needs to be a linear function, if it is not a linear function, meaning that the variable, in this case x, cannot have a square or a third or any power, it needs to be linear, then this integral always results in a divided by b, or you could even say bx plus c, but you have to derive this, times e to the power bx plus c. And why is this the case? This is the case because if we derive this function again, you would use a chaining rule and multiply with the derivative of its power. And the derivative of its power should cancel out what we have here, so we obtain a times e to the power of this back. So that's why we have to divide by exactly that term that we would add if you were to derive the function. So that is how you integrate your e power. So if we do that here, we get the following: 1 over t0. We open a square bracket, and now we're just writing down that rule, 1 over, now we have to derive the power, and that's why we also added the minus in front of it. We get I 2 pi times divided by t0 times k times e to the power of minus I 2 pi by 2 t0 times k times t, where we're filling in 0 and a half t0. Now, we're going to fill this in, so we get 1 over t0 is... We're going to fill in half t0. If we fill in a half t0 for t, well, the first term, the 1 divided by etc., stays the same. So we get 1 minus 1 divided by I 2 pi divided by t0 times k times e. Well, if we fill in half and t0, that would mean that this t0 gets removed, because t0 multiplied with 1 over t0 cancels each other out, and this 2 times a half also is removed. So we are left with minus I pi k, because we filled it in for t, so t is also gone. Minus, when we fill in a 0 for t. But if you fill in a 0 for t, that means the whole power of e is 0. And if something to the power is to the power of 0, it is 1. So anything to the power of 0 is 1. A to the power of 0 is 1 for every a there is. Now, we have left minus, or in this case not minus, because we get minus minus, so we get a plus 1 over I 2 pi divided by t0 times k, and then times 1 actually. So this is what we have. Good. Let's take out the big fraction that's in front of it for both terms. And multiply that with 1 over t0. So we get 1 over t0 multiplied with 1 over I 2 pi t0 k minus e to the power I minus I pi k plus 1. That's what we are left with. And if we multiply these fractions in front of it, then both t0s will be removed, because you get t0 times something divided by t0, so they will cancel each other out as well. So what we are left with is 1 over I 2 pi k e to the power minus I pi k plus 1. And this is good. This is nice. Now our question is now, how can we rewrite this? Well, e to the power minus I pi is a polar number. And if we recall in our complex plane where that takes place, pi is, this is an angle of 0 and an angle of pi is here. So the complex number that is associated with this is again minus 1 plus 0i. So this answer is actually minus 1. So we get the whole fraction again, I 2 pi k, multiply with not e to the power, but minus 1 to the power k plus 1. Now, if k is positive, that means if k is even, that means we get minus 1 times minus 1, which will be 1. In other words, let's write it down to the right here. If we have this is 1 if k is even, and this is minus 1 if k is odd. For k. If k is even or odd. So we know we know that we have two scenarios, because if k is odd, then we get inside these brackets here, we get minus 1 plus 1, which is 0. So if we make cases, we get 0 if and only if k is odd, because then it will be minus 1. But if it is not odd, what we would get is 2 divided by I 2 pi k. But even this, the two 2's in the numerator and denominator cancel each other out, so we would actually get 1 over I pi k. This is for every k that is even. So now we know what complex signals we got. And we know that we know our fundamental frequency with this, and we know what complex signals or complex exponentials we need to write down to represent this square function exactly. And as we can see, because this is our cases, k is odd and k is even, k will go into infinity. So we have infinitely many terms to obtain this square function. And to give you a nice visualization of how this looks, there's a nice interactive plot I have here that shows us a nice sign, and we can add different signs, and if we add them together, we see that the result gets changed further and further. And if we add infinitely many sinusoids, we see that we actually get the square function back. Now this is a very nice property that Fourier said. If I have a periodic signal, I can remodel it with infinitely many complex exponentials if needed. And as you can see, is the more sinusoids we add, the more it looks like the square function. And this is a very interesting and very well-used property that was developed by Fourier, which helps a lot with recording of voice messages and replaying voice messages and anything. And we will see how this is done better in next videos about aliasing and sampling and reconstructing those signals.